Um, okay, let's start. So again, we have a lot to cover today. Any questions about the homework at the moment? Any critical questions? All good? Okay, that's good. So our plan for today is to quickly finish system calls because we already understand exceptions and system calls will be implemented as one of the interrupts. We kind of talked about it already. And then start a new lecture on how we create a process, essentially, what's inside the exact system call. So, okay, good. So last time we talked about the interrupt passed through the kernel, right? So we remember that interrupt saves a bunch of stuff, and I will remind you in a second. But today, our goal is to understand how system calls are implemented, right? So system calls are controlled invocations of the kernel, right? So it's kind of like a function which you invoke, like a printf, but instead of being implemented in the same address space, where you can just simply do a call instruction and directly jump to that label, following the calling convention, right? System calls need to protect the kernel. So because the idea is obviously that you can only enter the kernel through a specific entry point, right? Why is that? Do we understand that? Or not? Yeah.
Protection and sanitizing the user.
Exactly. So for example, what you said protection, right? So, but what we really mean is that imagine there is a hypothetical mechanism which allows you to call across the privilege level. And such mechanism actually exists, I think, right? So, and multiple probably exist actually. But imagine this is your system call, and it has an entry point. Let's call it entry. And in the beginning of the system call, you have some code which checks whether the arguments which you pass into the kernel, so for example, the address of a buffer which you pass to the kernel actually points to the user address space, right? So it's a critical check because the user can pass any number as a point, right? And of course, if the user can somehow bypass this check and start execution of the system call from after this check, you can do anything with the kernel. You can pass an address of a page table directory, right, as an argument, and just simply say, okay, override the page table directory. And so that's not okay, right? So that's why the kernel always needs to start execution of a system call from a well-defined entry point, right? And there are multiple ways in modern hardware to implement this idea, but we're gonna use interrupt because we say, look, if this entry point is a vector 64, which matches this x40, then everything is okay. We're gonna follow the regular interrupt path, then land on a system call code, and then check the argument, and then do the system call, right? So this idea is clear. So this is kind of like this is the idea of protection, which you mentioned. Okay, so let's take a look. So again, in the past system, the interrupts were like almost the only mechanism to trigger this change, right? Because the magic of this int instruction is that you can configure the interrupt descriptor table entry in such a manner that it switches your privilege level. Remember how? So we have in the interrupt descriptor table, so if you have the whole table, and there is an entry, for example, for the system call for x40, there will be two interesting fields. One is a pointer to the handler, and the other one will be a code segment selector, right? So this thing will go and chooses an entry from the GDT. This is IDT, and this is a global descriptor table GDT, and you can choose an entry which specifies privilege level 0, for example, right? So privilege level 0. So even if you are running at privilege level 3, you say invoke int 64, the machine will choose a new code segment which was privilege level 0, right? So you switch the privilege level. I wanted to make sure that we still remember it, right? Okay. And x86 uses, as I keep saying, vector 64 for implementing system calls. Of course, you can choose any other unused vector, so you cannot use one which is reserved by Intel. You cannot use the one which is reserved for IRQs, those like physical devices. But other than that, you're free to choose any of them, right? And x86 just made this choice. So Intel Linux, for example, uses x80, right? So again, just a choice. And I should probably say, because many people will see it later in their lives, at some point, Intel understood that the interrupt transition mechanism is a little bit heavyweight. And I would say that I think handling an interrupt adds an overhead of something like 350 cycles alone. I don't actually know what Agner Fox sells in his tables. I haven't checked recently. It's a good idea to check his document. He probably measured this instruction as well. I measured it myself because like I cared about it. And so did many other people. And they said, okay, look, can we do something better? Because going through the IDT, going through the GDT, TSS, it adds time, right? And so Intel added two additional instructions, or rather, Intel added sysenter and AMD added syscall, which are roughly equivalent and are supported. Like this is a mismatch, like a minor mismatch between the AMD implementation of x86 and Intel's, right? And again, every time I look, I forget the details, but roughly speaking, one originates from Intel, and other from AMD, and they both implement. I think Intel also implements syscall on some version of the instruction set, like for example, on 64-bit instruction, but not on 32 or something like that. Are they? Yeah, probably have a different code, so the machine can distinguish between them. Again, those details are not very important, but this is a faster mechanism which bypasses this interrupt transition mechanism, and kind of what you can do is there's a special register which says, okay, this is the entry point, right? Like I was saying here. And let me change the color here for a sec. So the register says, okay, this is the entry point. If you invoke sysenter, your execution will go here. Sysenter will save, I think it only saves instruction pointer, because this is what gets changed, right? Because you immediately jump to the entry point. And the funny, ironic part is that this instruction pointer, I think it's put in the ECX register, which is a little unusual because again, you cannot trust the user stack, right? So the user stack might not be present because user might be malicious, but ECX register is always there. So the hardware just pushes the AP in the ECX, right? So stuff like that. And they change and they also like save a couple of other things. I think they don't remember the details, but one would imagine they can save CS if you change the CS segments and stuff like that, right? Code segment. So I don't cover it in this class because the transition with this is a little cumbersome, and you have to combine, because interrupts are still there. meaning that a device can preempt you and you have to then exit. You have to distinguish whether you enter through a sysenter or enter through the interrupt into the kernel. So again, I'm pretty sure that if you ever interested, you will be able to quickly figure out the details, but I'll skip them. So I will only cover the interrupt entry mechanism, right? And just to be clear about it, I said that if this one takes 350 cycles, this center will probably round trip to the kernel will be something like 130 cycles. So it's a significant reduction in cost. And I think I saw machines which were like roughly in a 105 cycles range. So again, it's very, very fast at this point, right? You probably can optimize even more, but they haven't. Okay, so we got it. So int64 is our syscall entry machinery. So similar to how we looked at the timer interrupt, now the similar path for vector64. The only difference is instead of like being triggered by the hardware, there will be an explicit int64 instruction in your code, right? And this triggers the transition into the kernel, right? But everything else is the same. So you go through the IDT, pick the code segment, pick the handler address in a kernel. The code segment chooses the new entry in the global descriptor table with privilege level 0. Of course, you need a stack. So hardware looks up the TSS from the GDT entry to the TSS. TSS has the pointer to the stack. The hardware happily saves these 5 things on the kernel stack, right? And after that, you start executing the vector64 code, very similar to how we did for the timer. In fact, identical, right? And this is what you will have there. So vector64, a label, as I was saying, generated automatically with a Perl script. PL stands for Perl. No one uses Perl anymore, but it was a popular thing before Python. It's the joke was it was a write-only language. So you can write programs, but it's very hard to read them because the syntax was so cumbersome. Many people disagree on that, but fine. So I cannot. I mean, I used to be able to read Perl with difficulties, but not anymore. And so this generates vector.s, right? And this is the entry, right? So again, similar, since int64 doesn't push an error code, they push a fake error code 0 on the stack to make sure that the stack is the same shape as during the interrupts or exceptions which push error codes. They push 64 on the stack to make sure that they later on can understand that they are executing interrupt 64, jump to all traps. Everything is identical to the previous lecture. This is how your stack looks like. These 5 things are pushed by the hardware. Vector32 pushes these 2 things. There's a bug, 64 here instead of 32, right? And you're currently executing 64 label, vector64 label. And again, it's full of bugs here. Guess I probably was copy-pasting. But everything else is the same, all traps, save all the registers, make sure that we have valid segment registers here, push the argument to the trap frame on the stack, and call the trap function. And now you will be in C, right? So we've already seen this C function. The stack will now look like this, and this part of the stack is called the trap frame, right? So cool. But of course, instead of going and executing, remember we executed the timer last time. In a switch case, they have an if statement here that says that the trap number means equals to 64. Then sure, let's start processing the syscall. There is a little bit of a management code here. So we're going to talk maybe later about how stuff gets killed. So if the process is killed, they will process exit. Otherwise, they remember the pointer to the trap frame on the current process data structure and enter the syscall routine, which will actually implement a specific system call. Syscall itself, again, how does it know which system call we execute right now? Because 64, the interrupt itself just doesn't code which system call specifically we are executing. So they came up with and you feel free to come up with your own calling convention, right? But it's not unusual to pick a register like x86 picks register EAX, which holds the system call number, right? And each of these system calls like read, exec, and so on is assign a number, right? And you essentially say, okay, if I want to invoke sysread, I will put a specific number which matches sysread in the EAX and then do int 64, right? So that's kind of not surprising. So where do we get the EAX register? Remember, it was saved. Okay, let me ask you a question. So how was it saved specifically? EAX register. I used to ask this on the exams. Yeah. Do you remember which instruction pushes? Push all, exactly. Push all. So this one is not pushed by the hardware. So it pushed on a stack by the push all instruction inside all traps function, which is here, right? And so this is how we access. Since we already saved the trap frame into the process data structure, this is called function is void, right? So you say, look, okay, I got it. I know where the trap frame is on the current stack. EAX is there too. So this is my syscall number. And after that, okay, I'm good to go execute all like the system calls, right? So you do a little bit of sanitization here. So it's also part of your kind of security. You say number should be greater than 0, but less than the number of supported system calls in a system, right? And actually, a system call has to be actually initialized, because if it's null in this table, in a second, we will take a look at the table, then we cannot execute a null register. So that's kind of logical sanitization of this argument, right? So, and the way we implement execution of a specific system call is that we have array of function pointers, right? So again, a little unusual, but okay, everyone can imagine there is there can be an array of a function pointers. You choose an entry in this array. We already checked that it's not null. And this is the syntax in C to invoke this function. So it's a void array of pointers to void functions, right? And you execute them. So like, for example, this is how this array is initialized in x86, right? So this is the syntax to define it. So it's a function pointer. Again, funky syntax, but whatever. It's better than Perl, believe me. So it says like it's a function pointer to a function which takes a void argument and returns an integer, right? And all system calls, despite the fact that they all have different number of arguments, are defined as those void functions. And I will, in a second, I will explain why it works this way, right? But that's fine. So that's kind of like this polymorphism. You say, look, I reduce any system call to a void function, but then I will recreate the arguments back, right? So, but that's normal, right? So, and again, if you reduce the font size a little, you can actually fit all the system calls on a screen, right? But I just wanted to make sure that you see the syntax and stuff. Question?
The author of the kernel of the figure.
In a second, we will discuss how the arguments are passed. So it's a good question. So yeah, because it's totally not clear. They came out, you have to come up with a new calling convention. They do. So I will explain it in a second.
So the system calls are operating system functionality.
Right.
Okay. But the sysenter / syscall instructions, those are hardware. But
correct.
They'll, irrespective of which hardware you're on, they'll eventually just bring you back to this logic.
Right.
In the operating.
Correct.
So it's just a pathway thing, not anything.
Correct. So it's kind of, and in fact, x86 doesn't support sysenter, but I think I did it for whatever reason. For some specific research reasons, I did it once, extended x86 with support of sysenter, just to compare the performance on real hardware, how much faster. I mean, x86 is kind of, it has an interesting history. So despite the fact that it's a research operating system, it actually showed up in a couple of high-profile research papers from MIT. So there was a paper on scalability. They essentially were studying, imagine you have a machine with 128 cores. The question is like, where is your bottleneck? Like, what really causes a slowdown? We cannot reason about it right now because we didn't really cover synchronization. We didn't really cover scalability bottlenecks. We will a little bit later, right? But they used SV6 as a guinea pig and essentially said, okay, we're going to study the system call interface because it's representative Unix interface or POSIX, right? So it's not really like full-scale Linux. It's very hard to understand what's going on. But here we understand what's going on. And it was there in that paper. They had another paper, which then later on, a student from MIT went to, as a professor, to University of Washington, and he was actually working on formal verification of operating systems, essentially making sure that implementation of a operating system is correct, meaning that it is equivalent to a high-level mathematical specification. Let's say a state machine which says, okay, when a system call executes, your file descriptor table is updated in this manner, and whatever the C code you wrote actually does what it intends to do. So it's interesting. And so I also was using x86 as a kind of playground to understand specific performance limitations in hardware, like how fast you can enter the kernel, right? Because the code is so simple that you can, if I don't like something, I quickly rewrite it, and nothing else breaks because it's so simple that usually can maintain all the invariants. And I did it as well, right? But x86 doesn't support sysenter, only interrupt as a mechanism to enter the kernel.
But that confuses me a little bit because should it, like, is it the hardware's responsibility to know where it wants to be? And wouldn't that entry point sort of be similar, irrespective of whether we interrupt like 0 spot we go to?
Correct. So remember, this is how we initialize the interrupt descriptor table. Again, this is to make sure that we can figure the entry point correctly in case we're using an int something mechanism, right? So specifically, we said all the entries in the interrupt descriptor table are those. The user cannot invoke them because they are privilege level 0, so you cannot do int 128. But one entry is special. We will configure it with privilege level 3. And of course, what we do here is we say, look, we have this array of handlers, right? So this vectors array is initialized to point to vector 1, okay, vector 0, vector 1, vector 64, right? So this way, when we boot, before enabling or before starting a single process, we initialize this entry path, right? So we cannot be abused later in the kernel, right? If, however, we would support a sysenter, we would probably have another function, something like sysenter init, and we would say that, okay, the special register which contains the entry point will point to, since the calling convention will be slightly different between int64 and sysenter, we cannot point it directly to this vector, but we would create a specific like syscall entry, maybe code it in assembly, put it in a separate file, and just make sure that we can handle this funky calling convention where this instruction pointer is saved in the EAX. We probably don't have a kernel stack because TSS is not involved. So we have, before saving all the registers, we have to set up the stack, and we would carefully code it in syscall entry. But eventually, I would imagine we would still call something like a trap, just to make sure that we have then later on have uniform processing, right? But so that's how it would be done. Right, that's clear now? Okay, cool. Any other questions? Okay, so we have this table, and as I was saying, if you execute a system call, since it returns an integer, we write back to the EAX register, simply override this entry on the stack, and later on, when we exit from the interrupt, we will restore this entry on the stack into the EAX register, which kind of matches the calling convention, original calling convention. It's convenient, so we pass the return value from the system call back into the EAX register. That's how the user code will see it, right? Okay, so not super hard, and we can of course fail. So if this check fails, then we will print something on a console saying that the user tries to abuse us, and we will return -1 as a return value, saying that we failed here. That's fine. But again, so you asked the question previously. So how is that with passing arguments to the system calls? Because all the functions are defined as void functions, right? And you say, well, that's fine. I probably still want to pass arguments on the stack because my programs expect the system call calling convention, right? So it's probably fine to push those arguments on the user stack. So for example, if we have an exec system call here, we will push argv on the stack, push the what is that? What is it we're pushing? Init. Why do we push init? Probably it's probably a line from the book which invokes the init process, like execs into init, right? And I will show you this line later on. So like, sorry, I apologize. And so this is the, what is this? Okay, let's come back to it later on. Forgot about it. Probably put this slide like a couple of years ago and now I don't remember what's going on. But the key point here is that you really like move the number in the EAX register and then do the int 64, right? And you say, look, it's probably feasible to code your C programs with these snippets of assembly, but it doesn't look very intuitive, right? Even myself, after so many years of looking at Swift6, I cannot figure out exactly what this all means, right? So a couple of pushes on the stack, but what is it really, right? And so instead, of course, the kernel does a little bit of a plumbing. So on a real Linux machine, right, this plumbing will be inside libc, right? So because you also call write system calls, you never even thought about how it was invoked, right? You just say, okay, link against the function. And so the kernel will define this user.h file, which is, okay, look, that's my interface, right? So here is like all my system calls, like fork is a void, the write has 3 arguments, integer, void, pointer to the buffer, integer is a number of file descriptor, and this second integer is a size of the buffer, right? And exec here is a pointer to the pass to the process, and this is argv array, which we just seen a second ago, right? Sure. And if we, like, again, we have a C compiler, which follows the same calling convention, right? So from this header file definition, C will generate a call side. So for example, if inside your cat.c file, you call a write system call like that, saying, okay, please write something in a standard output. Here's my buffer and here's the size of a buffer. The compiler can easily generate this calling convention, right? Do we agree with this? To like push everything on the stack that was similar to what I was just showing, right? And then of course it says, okay, I get it. So there must be a write label somewhere in your code. Since you promised, so I will generate this symbol. It's not yet resolved. You know, when we're going to be linking, we will figure it out in our object file, right? But other than that, it's kind of good, right? So sounds reasonable. And of course, if you have slightly different versions of GCC compiler, you might on your own, like if you disassemble your own system, it might look a little different, right? So for example, here, another implementation of the same idea, but instead of push, they reserved space on a stack, and like essentially what they do here is, or they just say, okay, this is the argument 1, we're moving this 1 onto the stack. We're moving the buffer address, which is a global variable in this code, moving it at stack +4. This is GNU syntax for ESP +4. And this one is we're moving n, which is inside EBX, to ESP +8, right? So kind of equivalent sequence. Okay, so it all sounds good, right? But it's still a little bit unclear because the compiler knows how to generate the call site invocation, right? But what about this int64 sequence? How would you do a plumbing for that? Like imagine you are a designer and like I ask you a question, like, can you come up with some kind of a freaking C assembly and everything to make sure that you can invoke those system calls and it's relatively transparent to the user or completely transparent? C question? No C expert. Yeah, so generate some kind of a wrapper. How would you do that? Yeah, so you can say, look, I can use an inline assembly to generate, essentially what you want to generate is something like literally int syscall int 64 and maybe move some number into EAX, right? Because you say, well, okay, if I want to use Intel syntax, maybe I should erase this and write it slightly differently. So EAX, some number, let's say 5, right? So you need this sequence and you need a label saying something like right, because then compiler will, we just saw that it generated the call side. The compiler will be looking for this right label, right? Because in the object file to link against it, right? And literally your sequence should be something like this, right? Agree? You had a
Yes.
Mhm.
Since now the kernel knows what system call is being issued, maybe we could pass away for the actual system call implementation to identify where the arguments would be.
No, hold on. We really need just this. So maybe I confused you a little bit, but what x86 is doing is just following. So it says, okay, I will have a assembly file, uses.s, and I will use a macro to define each system call. The way it reads is that the way you invoke it is the following. You say, I want to define a fork system call. You pass a name here, which will literally just generate this assembly. So it says, okay, a name, and it says the name will be global, so you can link against it from other files. And here you just use a little bit of a magic. You say, look, it's a sys, this is a concatenation symbol, so it will result into sys, if you pass fork, sys_fork, you loading this into the EAX register and literally invoke the int 64. After that, you simply return, right? And having this macro, you just go ahead and generate all the system calls in the system, right? That's the plumbing. So you can do it by hand if you like, but maybe it's a little bit convenient to use this macro mechanism to generate stuff, right? Again, C has a very naive support for macros, right? It's very easy to break. But other languages like Rust have decent macro ecosystem, right? So they're hygienic and stuff like that. So you will see, I mean, the reason I talk about it, that you will see more of these tricks in your life later on. So, I mean, abusing this too much will probably confuse you a lot, but using it a little bit, you can conveniently shorten the code. So for example, in your homework assignment homework 3, where we were defining a page table, I could have gone with the pass of macros. And instead of saying, let's run a loop which initializes the page table, I could, for example, say, I will create a macro which expands recursively into starting from a specific address, I would be adding specific offsets and initialize the page of a page table statically, if I like, right? So again, just one way to do it. Okay, any questions about this one?
The argument passing happens inside the 64.
The argument passing happens, okay, we will talk about it in a second. I'll ask you another question. So this code runs where? In a user mode or in the kernel? User, good, why? Well, because we haven't entered the kernel with int, right? Exactly. So I just wanted to make sure that all this plumbing, which we cover, runs inside the user. It runs outside of the kernel. On Linux, it will be part of your libc, against which you link. On x86, it's called uses.s, right? And so now this, again, if we remember my example, so in which, this one. So the compiler from the header file, compiler generates the call side. Then it calls this label, call write. This macro provides this label. So I don't have it on the screen, but this is how it looks. So essentially in your code, in the cat.asm, if you disassemble it, there will be a label write generated from this macro, right? And which says, okay, I will move, it's x10, so probably 16, into the EAX register to say that the user tries to call system call number 16, right? Which is the right system call, and then invoke immediately X40 into X40, right? And at this point, you transition into the kernel, right? And then the kernel does an IRAT. You find yourself on the next instruction, which is return. You return from this label, and which means that you find yourself here right after the invocation of this right system call, or if you like, on the next instruction of this C file.
So to do it IRAT again, this is totally tangential, but with the syscall function, that's a C function, returns normal, right? How does it know to return specifically to the user process with the stack change?
Say again.
So I'm just going back and noticing on the syscall function. That once you're done calling the actual syscall handler.
You mean here?
Like,
this one?
yes.
Okay,
So
good.
at the end of this, it returns. So this being from the kernel, how does it go all the way back to the user?
Okay, good. Correct. So, right. So at this point, we have two stacks, right? So don't forget about it. So right now, when you return from this function, you're executing on the kernel stack. This drop frame also sits on the kernel stack, right? And so what we've done here is that we adjusted a value on the kernel stack, which says, okay, EAX equals to something, right? So if I go backwards here, this EAX will be sitting somewhere among all registers, right? This is where we wrote it, right? And if I go slightly backwards again here, it will be roughly somewhere around here, right? Everything what we pushed before calling in64 is sitting on this stack somewhere here, right? On the user stack. And so, of course, we say, okay, we adjusted EAX value on this stack. How will we restore it to be on this stack, right? In fact, we don't need to restore EAX to be on the stack. What we need to do is when we return from the system call, and specifically when we find ourselves, let me show you, when we find ourselves right here, erase everything on this. Like at this point in execution, when we return back from the kernel, EAX should be equal to this value which we saved on the kernel stack, right? But remember how we exit from the interrupt. So I was talking about it last time, and let me talk about it again. So when we, for example, done executing a system call, or like last time we discussed, we were executing a timer. So we were sitting inside the trap function. Your call stack inside the kernel was vector 32, all traps, then trap, right? So this is a normal C function. When you start returning from this C function, you literally, since you called the trap here, right, inside the kernel, you return exactly here. You adjust the stack to adjust for this argument which you pushed on a stack. And then it's an assembly sequence. So you say, I'm gonna execute the trap rat. So that just continues this way. So after this instruction, pop all executes, and pop all restores all the registers, right? Since EAX was saved on the stack, pop all will restore it in the EAX register. Then you say, I'm gonna restore all the segments which were used by the user. I will adjust the stack for this two things which we pushed, trap number and error code, and I will execute an IRAT. And IRAT will pick up the last 5 things on the stack. This is the ones which were saved by the hardware, right? These 5, and will restore them in registers. And at this point, you are back in user because this instruction pointer was a user instruction pointer. This code segment was a user code segment, stack segment was a user stack segment, ESP was user stack, right? Any flags just restored.
Thank you. I just had a misconception that all of these is really chunks only used.
Well, you can stitch it differently. You just have to be careful to make sure that you implement a symmetric sequence to make sure that At the point you execute IRAT, you really just stack points here, ESP, right? And then you will be just fine. And okay, so that was a good question, just because I agree, it's a little bit unclear, but again, this is your whole pass through the kernel. So you say, well, this is for the interrupt, but for the system call, it will look exactly the same. So you say, I'm starting from int64, it takes me here, I land on the vector 64, then I jump to all traps, right, to save all the registers, then I jump to trap, then I execute some functions in the kernel, now no matter which ones, but eventually I start returning, and so you return to trap, all traps, and at the end of all traps, you don't go back to the vector 64, you kind of skip it, instead of you just patch the stack and immediately do the IRAT to return here to the user.
I thought was pretty brilliant because just pipeline do this way to just get your registers correct, and you don't want to like return back through the assembly.
Yeah, so, but again, there is a little bit of a design choice, so you can do it differently. You just have to have this mental model of what's on the stack at every moment of time, and then you can return. Okay, good. Any other questions? Okay, so we are then here. So we said, okay, we executed the system call. Like from this macro, we generated this label. We know how we enter the kernel. And yet I still didn't explain the calling convention, right? So okay, so how do we pass arguments to the kernel? So there might be multiple choices. You already seen how they were passed, but let me ask you a question. So how? Can someone explain it in English? Maybe someone in the back will volunteer. On a stack, correct. So remember, when we were calling the system call, like before calling this write label, we pushed all these three arguments on the user stack, kind of following the normal C calling convention, right? So okay, cool. So that's a good idea. So why not we essentially just really adopt this thing that we're gonna pass system call arguments on a stack, right? And let's take a look at the example at how the kernel really accesses them. Remember, the trickery here is that you invoke this write system call at user level as a function with three arguments, right, which returns an integer. In a kernel, syswrite is implemented as a void function because we said, okay, we want to have this polymorphic array. Everything is a void function, right? Every system call is a void function. How do we access those arguments? So the kernel says, okay, sure, I know how to do this. I can just use functions, helper functions, which will fetch those different arguments from the user stack. So, and here, the kernel of the, like, when it implements syswrite, it says, okay, I'm gonna follow those helper functions like arg, which fetches a file descriptor, argfd, fetches an integer, argint, or fetches a pointer, argptr, right? So, and what those functions are doing, they're essentially looking up at the kernels, at the user stack where the arguments live and sanitize them as they go, right? So let's take a look at the very first one. So argint is probably the easiest, right? So it says, okay, please fetch the second argument to this system call, right? What is it? File descriptor. Second starts from 0, 0, 1, and 2. So it's a third argument, but number 2. So they try to fetch this user n into the kernel variable n, which is a local variable defined here, right? So they say, okay, let's take a look at what the user passed us. Don't forget that we're currently running on a kernel stack, and those things are saved on a user stack. And so the kernel implements this set of helper functions, right? So for example, the one which fetches an integer works in the following manner. It uses yet another function, fetch integer, but it says, okay, by the way, fetch me something from the user stack. So here they start from the user stack pointer itself, right? Because it's on a trap frame. And we say, look, okay, I know where it is. So it's on a trap frame. We're going to skip the return address because the calling convention is broken a little bit, because remember, we called the right label, so there must be a return address on the user stack as well. So we skip this 4. And then we assume that each argument is an integer, and we fetch the nth argument, because if each is an integer, it's 4 bytes. So multiply by n will give us the correct address on the user stack. Do you understand this formula? Right? Okay, cool. And this is where we want to fetch it, in the integer pointer. So internally, fetch int has to do a little bit of work. So you don't trust the user, right? Because the user can supply any address in this stack, because when the user invokes int64, before doing that, ESP may be set to 0, to FFF, and so on, right? Some unmapped page, we can crush here. So the kernel is very careful about it. So it sanitizes the arguments. It says, okay, let's take a look at the address which you're trying to access. And we will run this check. We say, we currently know the size of the address space of a process. It's contained in this SZ field. So it stands for size. We'll see in the next lecture, we'll see how this SZ is affected by different system calls, right? So it has to be, if address is greater than the current size, or by the way, since you're fetching the integer, the whole integer has to be within the address space of the user. So if address plus 4 is greater than the size of the address space, then we immediately exit and say that the user tries to cheat here, right? If not, however, it's a safe to access. And so they say they dereference the address and save it in a locally passed pointer, right? So, and this integer n ends up here. And since we called it from here, and this was called with n, we get this value from the user address space, right? So just to explain how this size works, so x86 create the following address space. So they load everything at address 0, like the process stacks, process data. There will be process stack and a specific page, which is a guard page, which will be mapped as not user accessible. So if you have a stack overflow in x86 and you're running out of space on the stack, you hit the guard page and get a page fault. Essentially, at this point, you know that there is a stack overflow, and the heap will be growing this way. And this proc SZ always points to the very last page of the user heap. So the check which we were running effectively was saying that this integer is contained within the user address space anywhere. So maybe it's in a process text. Then something bad will happen. Maybe the kernel will overwrite your program if you do a read system call, for example. And so we made sure that there is also no partial integer, like essentially spill into beyond the address space, right? So this one. So we're passing 3 arguments, and we looked at how the integer is fetched.
Yeah.
So argument number 2.
I was looking at like what we passed in the.
Okay, so we looked at the how we fetch an integer. What about what I wanted to ask? What about if we argument number 1, which is this buffer? So kernel uses this argptr function, which takes the number of the argument 1 in this example, a pointer where they want to have a sanitized pointer to the user buffer. So user buffer points to somewhere in user address space, and this p will be pointing here after sanitization. And it's n, which we fetched here, which we already know that it's safe, and because it's our variable, is the size of the buffer. So how will you sanitize a buffer? So what's inside this argptr? What kind of checks do we need to do?
The length.
They need to make sure the buffer is checked.
Correct. And so we need to make sure that no matter what pointer the user passes, the buffer has to be somewhere inside the address space, right? But there is a little bit of a trickery here, because how do we pass this buffer? Like, again, let me just make absolutely concrete figure here. So this is the process stack. So there is the pointer which we pass to the kernel. And the buffer might be somewhere here on a heap, right? So this pointer has to point to here, but we needed like a two-step thing here. Correct. And this is exactly what the kernel is doing. So they say, look, when we want to sanitize a pointer, we'll first use this argin function to fetch the pointer as integer. And it's safe because the kernel may cheat. So not the kernel, the user may cheat. Instead of passing a pointer here, they say, well, I will pass a pointer here. And then if you're only sanitizing the buffer, the kernel will crash by trying to access the argument, right? So that's not okay. And so they do that and say, look, okay, we first fetch an integer. And then when we fetch the integer into this I variable, we're going to check that it's within the address space, and the I plus size, which we passed here, is also within the address space, right? And after that, we say, look, it's safe to use it at this point, right? And essentially, yeah, and that's it. And so I mentioned like a couple of other functions, like a kernel sanitizes a file descriptor. It's kind of like similar deal. You say, first, I will check that the number which they're trying to pass is like within the address range, but then I will check it against the user, against the file descriptor table of this process, and I will make sure that actually this file exists, and I will pass the pointer to a file data structure from this table, right? And then I can call a function which is file write, which implements the write into that file. Question.
Yeah. Currently inside the PTR, we only see the check of the lower bound. How about the upper bound?
How about the upper bound?
We only check the lower bound. Yeah. You should also have an upper bound.
This one, right? What is the lower bound? Lower bound, the address space is from 0 to proc SZ, right? So we need to make sure that we are within this range, right? Agree?
That's full buffer.
Yeah, so and that's the full buffer, I plus size, right?
How do you get that?
Say again? The size is passed as an argument, right? So you check for both the fact that the entire buffer is within the address space, right?
Yeah.
But there is a, like, I'll ask you a different question, but okay, go ahead.
Because
Look, I'll ask you a different question before answering yours. I apologize. Why not just this check? Because it checks that the I plus size is less than proc SZ. So why do you need this second part of this check? Trickery of kernel programming. Google interview. Correct. It can wrap around. So if this I, for example, points to somewhere here, right? I plus size will be correctly wrapped around and points to the user address space. So that's why they say, hey, hold on, need to. All right, let me quickly restart my Wacom tablet. Now I learned how to do just one simple command, so I hope it works now. Yep. Where is it? Wait, guys. Get back. This, oh, this. This is Zoom. Where is my lecture? This one. Yeah, so if you just simply say, if this is I, and this is I plus size, it may pass the check for I plus size, right? But you need to make sure that you don't wrap around. That's why they essentially say, look, I also should be within this range. So this is kind of like showcases the difficulty of these checks. Even for a simple one pointer check, you have to do this nonsensical overflow reasoning, right? It quickly escalates if you have more complicated cases. And that's why essentially kernels do have bugs, right? So it's Like it's pretty easy to miss a check like this in your real C code in a kernel. It's not just the kernel, it's like web servers, anything, anything what will be exploited. It's not easy, right? So it's nice when the language handles it for you, like guards against overflows and stuff like that, but C doesn't, right? So that's why. Now question, sorry.
I'm guessing all the systems are designed to only pass 4 byte IDs.
Sure.
Otherwise, IDs wouldn't work.
Sure, yeah.
In module kernels or full-fledged kernels, do they account for various types? I'm guessing if
You probably can, and I don't know for sure, but you can also imagine that anything what is a different size can be passed as a pointer, right? So but if you really like want to support a different language, for example, Rust bindings, and you say, look, I want to pass tuples or something what is larger than integer. So even like data structures in C, like you say, I want to pass a struct something as an argument. I think typically it's not done, again, for this very reasons that sanitization of the arguments becomes complicated. Yeah, so it's really semantic complexity doesn't disappear. So even if the interface is really like, imagine we can wrap this, like, or more specifically, imagine we have a language which has support for some kind of a range primitive, which says that buffer and a size is a single type, and you say, I want to pass this buffer and a size to the kernel as a single type. I would rather say you still need some kind of a marshalling thing, and it's your design choice. So maybe you will, in the end, will implement marshalling as 2 different things, as a size and buffer, and then check in similar manner. Even if you don't do it and pass a real type, you will still have to sanitize the specific type in a similar manner. And that comes back to you, imagine you programming in Java and it's like over the network, marshalling over whatever, Google protocol buffers or something like that. They do handle a lot of sanitization, most likely almost everything, but at some point with your custom types, you might run into problems, right? So that's where the real life is, unfortunately.
Right, those 3 variables within that scope are uninitialized. Does that somehow bring it back to the trap frame? What does that do?
Which variables? Like
F and P.
F and P?
Yeah.
They are sitting as local variables on a kernel stack. They are uninitialized, right? But after you execute those functions, they will be initialized. That's the contract. They also carefully choose the order of this evaluation. So for example, they first evaluate N and sanitize N, and only then go to sanitize P because it uses N as an argument. So there is a dependency between them. I would not argue to write it this way. Again, probably their logic was to fit it on one line to reduce the number of lines. For transparency, I would say I would sanitize them as different lines, one by one, returning different errors, or like returning the same error, but at least knowing which check fails. As a programming style, you can argue about it. I mean, I'm not like an expert on programming style either, right? But the contract is that you will never reach this function without initializing those correctly, right? Again, it's a 2-liner, but even here, we can say, okay, is it always true? Like, is this contract always holds? Good luck to you verifying it, right? So, and that's essentially the basis for essentially formal reasoning about the system correctness. So if you, and this is how the kernel bugs exist, right? Essentially, you imagine you passing like 10 arguments and you forgot correctly to do something correctly in this check. Then you're reaching this function. One of those arguments is uninitialized, and you're pointing to like kernel memory or uninitialized user memory. And that's the bug. You crash the kernel. Okay, agree? Okay, cool. So we are actually done with system calls. So, and done with interrupts as well. So it's a huge success because why? So we covered 2 things, right? So remember, the kernel itself, I keep saying that it doesn't have that much kind of, if you try to define what the kernel is, so really the goal is to kind of boot into something like whatever your the Doom or something, whatever you want to run, Doom or whatever, maybe something more meaningful, web server, and run it on the kernel and periodically switch between these two, right? So we have a timer interrupt, which, remember, I said, do you remember? It actually executes yield. And we will cover how this yield is implemented, how you actually switch. But kind of we see that the timer interrupt will cause one program to cease CPU and start executing the other program. We also now know the protection between the kernel and the user and between individual programs, right? So we know that this is CPL 3 and this is CPL or PL0, right? And we know that we can enter the kernel through the system call mechanism. And we are kind of like almost, I would say, halfway to start running something real on whatever, on this Hello World kernel, which we kind of build or building, right? So that's a useful set of primitives which we learned, right? Any questions about interrupts and exceptions?
What's the instruction to change the CPU?
What's the instruction to change the TPL? Who can answer me in class? I know a couple of instructions, so I use 2 of them. So which ones do you guys know?
Does interrupt do that?
Correct. Int instruction changes CPL because it goes through the IDT, and the entry in the IDT will choose your CS, and CS will point to the GDT, and the entry in the GDT might have a different privilege level, like for example, 3, right? That's how the change happens. That's instruction number 1. What else? What other instructions we know?
IRET.
Correct. IRET will do the opposite to int. These 2 instructions allow you to change CPL in a meaningful way. If I stress you and ask you, can you change CPL in some less elegant way? But literally you will change it. How can you do it? Well, we have syscall, which we didn't cover really, but we know that it exists, syscall and then sysret or something. What other ways? What else will change your CPL?
Check.
A check? Which check?
Check.
Trap. Which trap? There is no trap. Trap is not an instruction. How else can you change the privilege level? Is there a pseudo instruction? No.
Long jump?
Pseudo. Okay. Long jump? No. Maybe long jump is a. Let's set it aside. I don't know how it works. But literally, like a move instruction can change a CPL, right? Because if you're moving from somewhere which is like X, F, F, which is not on your page table, that will change your privilege level, right? Because it will trigger a page fault, right? Now we understand it. And that's exactly how your SAC fault works, right? When you crash your program. What else?
But then isn't that like saying any failing instruction will trigger?
Correct. Yeah, and that's what I was trying to say. So any instruction which triggers a hardware exception will trigger a privilege level change in a normal system in which configures handling of this handler exception at different privilege level, right? So here we say, let's say normal kernels will put 0 here, but maybe some of them will put 3, or maybe you are in the kernel already and seeing an exception like division by 0, then you stay in a kernel, right? So just the reason I keep this discussion going, that I want you to make sure, I want everyone to understand that there are ways to change privilege level, and there are some good ways when you really intend to do it, and there are some ways where you don't intend to do it, like with any instruction which is failing, right? And you can push this argument further, and maybe I keep mentioning that there are these hardware level attacks. You might like trigger. Maybe you can trigger something like a hardware exception, like machine check exception, by overheating the CPU or something like that. So in theory, it's possible, right? So, and I told you that there is a range of attacks which are called row hammer attacks, which these like drain the charge on the memory in the DRAM bank. And because DRAM banks, it's a set of capacitors, and at some point the capacitors lose power or lose charge, and you lose data. So DRAM actually reads the line and writes it back, right? So we know it from like primitive introduction to architecture class, hardware architecture, right? So, and if you say, look, hardware does it so often, but you really figured a way in software to drain these capacitors faster, then you can trigger a flip of a bit, right? So it's called row hammer. It's not going to send you an exception, right? Because it's transparent to the hardware, but you can really like attack, switch from.
It's sort of relying until speculatively executing that and then like rolling it back.
Yeah, that's this technique which you were describing is an exception. It's a trick to suppress an exception. So you want to trigger an exception, but then convince the CPU that it didn't happen. Spectre does it. Yeah, it's very elegant. Again, one of the papers which is so cute. Hopefully we can come back to it. But I just wanted to make sure that yeah. So overlaying Spectre on top of it is a good exercise. Let's see. We'll hopefully come back, but I mean, I don't know how many people read Spectre and Meltdown. Okay, good. So we got it. So there was a question, another question.
So I know when, for example, when we use the move instruction to access some memory address, that will trigger the segment fault. What exactly the process to trigger segment fault? The hardware will do the tracking or?
Yeah, the hardware will do the tracking. So essentially, remember, I'll go back to my fetch, decode, execute loop. You know, you normally execute an instruction, and essentially here you try to execute the move, right? And from some error. And the hardware at this point, since the error should go through the global descriptor table first, remember logical address, produce a linear address, then this linear address goes to the page table, right? So page table should be pointed by the CR3 and stuff like that, right? And in order to really fetch the value from memory, the hardware walks the page table. It like implements the same algorithm. So it says, okay, I will take this linear address, I will split it into 10, and 12 bits, and I will use these 10 bits to locate an entry in the page table directory. Then we'll figure out the address of the next level. First of all, if this is not present, it's already a page fault. If this is present, I will go to this physical address of this page. We'll use these 10 bits to walk it and so on, right? So this logic is actually on the CPU here. And it's in hardware because the page walk is on a critical path. So I think it's actually implemented as a collection of gates.
So you said the hardware will implement the page walk. So why we still see the page walk logic or function inside the x86?
Okay, so good question. So why did we, like, hardware does the page walk? So it takes any address which you provide, for example, as an argument to a move instruction, and resolves it into a physical address here, right? But x86 was using a function walk page directory, right? So why did we use this function? Who remembers? What was the purpose of this function? Which was kind of walking the page table. In fact, in your homework, I asked you to implement something similar. When you do mmap function, you have to walk the page table, right? No, like more specifically, if you worked on your homework and if you do something like if you write to a map function, which I ask you to write, a map says, okay, I take the virtual address and I really need to find an entry in a page table, which I have to update to physical address, right? So it's the same logic, but you first configure the system, and you have to, the logic of this walk function should match the logic of the hardware. Layout of page tables should match what hardware expects, but then it's just that you also want to manipulate the page table. You can imagine that the hardware can maybe provide you an interface which walks the page table for you and gives you this, but it's not done, and it's probably unnecessary as well. Because sometimes you walk it, you do it on a page table which is not currently active, and you're going to load it later. So it's impossible to kind of like, it's a chicken and egg problem, right?
Thank you.
Any other questions? Okay, we are almost there. So, okay, done with this calls. Since we still have 10 minutes, we can happily start our next lecture. Since we don't have. And this one is an interesting lecture as well. So again, in this lecture, the point is to learn how a operating system can create a process. There is a little bit of a chicken and egg here as well. So I first going to explain how exec system call is executed, right? So is implemented by x86. However, I did not explain how we create the very first process in the system. We're going to wait a little because in order to understand it better, we first understand how the context switching works from one process to another, how the scheduling works, essentially how the system chooses which process to run. And then it's very easy to understand how the initialization actually happens and how the very first process is created in the system. But just for a sec, remember in our introductory lectures or even on the system call interface lectures, I keep saying that, okay, exec does something, and later on we'll actually look at the concrete implementation of exec. So just to warm up, so what is that exec doing? Who can tell me? It does what? No. The other, that was fork. Fork is a clone, right?
No, it overrides the address space.
Correct. So it essentially says, okay, I'm going to find a program on disk. There will be some kind of an L file. And exec takes a pass. So kind of like whatever, /bin ls, for example, and some arguments to this new program. And we'll create a new address space and we'll load the L file into this address space, right? So essentially like text and data section, right? And it doesn't sound that hard, especially after we've done the homework too, on loading the L. That's why it was done, to specifically to warm you up and say that exec is actually not as hard as it might seem, right? Agree? Okay, so that's exec, but we'll take a look at the details. And remember that the address space which x86 creates consists of these two parts, right? So x86 chooses exactly half and half split. So this one has 2 GB boundary. So it leaves 2 GB for the user and 2 GB for the kernel. Remember, the kernel maps everything from physical address 0 with a 2 GB shift here, right? So up to the max available physical memory, which is called physstop, this one, right? And also maps this like IO space at the very end of the address space, although maybe device drivers are using it, right? And this part of the address space is a user memory. This is where we're going to load this L file. Agree? Right? And more specifically, right? So, okay, this is the kernel. We know how to create an address space, or at least we know how to create the kernel part of the address space, right? So specifically, when we were booting into main, the first function initializes the memory allocator, and the second function, kv-malloc, initializes a new page table with the kernel part of the address space, which maps this part, leaving this green part empty, right? Remember? So the kernel, we are currently running on a page table which has nothing in those addresses, right? Only these are mapped, right? Okay, and obviously our goal, like in this lecture, is to understand how this part of the address space is created, right? However, there's an additional twist. I keep talking about it, and I say that, and we now understand why. So when your user code executes an int 64 instruction, we immediately going through like some IDT and everything, interrupt transition pass, we land on a kernel. But we've seen that there is no page table switch anywhere on a pass, right? So we run on the same page table, agree? So now it's very concrete that in this implementation of the kernel, which we've seen with vector 64, yada, 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 I didn't skip a single bit, so there is no switch of a page table. And this is essentially the reason why we want the whole thing to be mapped in every address space, right? So just specifically, so you can execute a syscall in 64 and go through the interrupt transition, land somewhere in the interrupt handler in the kernel, right? Same page table, nothing gets switched. Alternatively, you're running here and an IO interrupt, like a timer comes in, and it also pushes you through a same transition on slightly different vector, but in a kernel, right? Again, we were very, very specific about how everything is constructed. So that's the logic, that you need those two parts, like the lower part and the upper part, right? So every process in the system will have the kernel part mapped in its address space, right? Agree with this? Any questions about it? Okay. And sure, so we know, we kind of have the outline. So this is what we want. If I ask you a question, how can we implement exec? So imagine we have this signature. It says, okay, there's a file, pass to a file which we want to execute, bin ls, a pointer to the argv array. I will explain like specifics of this argv array, but if I ask you how to sketch the outline. That's a good question, a very good question. So the question is, imagine you starting in this address space, right? In which, let me erase everything. And it's good to connect everything together. You are saying, I'm running here, I do int 64, that's my int 64. And I pushed like the exact system call number in the AX register. It feels naturally that you will never come back to this address space, right? Because you're going to be overriding it with bin ls, right? That's what you're saying. Okay, that seems fine. So who cares about what if we never come back, right? But the logical question is the following. What happens if there is a bug, or no, like not bug, but if you, for example, run out of kernel memory halfway through exec, meaning that you said, you started overwriting this memory, overwrite it one page, overwrote second page, and then suddenly kernel allocator says, I ran out of memory. What's now? In theory, exec should say, look, I will return an error. I ran out of memory, could not do an exec. But this address space is already corrupted, right? So you cannot really like recover it back. Okay, so a couple of meaningful design choices here is that you can probably do like backup of this stuff which you were overriding. But what x86 is doing, it actually will create a new clean address space for this new process. Like the process data structure will stay the same. The file descriptors will stay the same, but the page table will be different, right? And we now understand like kind of the connection, or we'll understand it a little bit better, but like an address space is a page table. So they will start by not, they will not destroy the old page table, then they will start constructing a new one. And they will reach a point at which they know we're not going to fail at this point. And after that, they will discard the old one. After you execute everything of the exec and you're sure that you can finish. At that point, they say, okay, it's time to deallocate the old one. But very good observation. Question.
Well, I guess like are you just copying the old page table and then getting rid of all of the pages in the user space so that they can't access it anymore? Because you're going to have to reallocate it, right?
Kind of. And I mean, again, there are multiple design choices here, and x86 follows the path of simplicity. So they will literally create a new page table, and they will, again, instead of like copying those entries, they like allocate new ones, which is wasteful. And they ask this question in a book or on the exam, how to make this optimization, how to copy those pages, but they literally will allocate this, like they will use the same mapping function to map all fresh pages. And at some point, there's just deallocate, just free the old one, saying, okay, we don't need it anymore. So it's not the best way to implement it. Arguably, it's like wasteful, You waste performance, you waste resources, but they do it this way. But that's one way to do it. You can do it differently, I guess. Okay, good. So, okay, so since we're so close, that's okay, but wait, so close, wait, 2 more minutes of discussion. So, okay, so what's the outline? That was my question. Everyone wants to go, but I still have what, how many minutes? 1 minute. So what's the outline? Like you're halfway there, so tell me.
So, I guess, the package space from fork.
No, we're not going to use fork. Exec is a standalone system call. I mean, technically speaking, you can play with fork and like use a fork as a building block, but it's not necessary. So literally, yeah.
Then once we have the memory, then first we'll have to create the memory.
Yeah, construct a new page table or address space. Okay, that's step number 1. So what's step number 2? Read the file, right? Read the elf, or like there is a couple of steps, like we know how to do it, elf header, program header, and start loading all these things in memory. You probably don't need to construct a full address space because you don't upfront know the size of the elf. So maybe you can combine these two and say, look, I will be allocating user pages as I understand, as I read the elf and figure out that I need more memory, right? Correct. So you have to maybe 2.5 allocate stack for the user, place the arguments on a stack.
And then I would encapsulate.
Yeah, you will probably have a proc data structure here, step 0, right? Runnable, yeah, runnable. And how do you start running? You will create a trap frame on a kernel stack, right? In such a point that user TF EAP will point, let's say, to main or the entry point of the process, right? And at some point, that's enough. At some point, you can IRET into it and it will start running. So that's the outline. So good job figuring it out, and we will cover it next time. So essentially, those steps are not as hard, but we will do them.
The copy the file descriptor should also be included in the exec, right?